In this last section of Chapter 2, we'll speak a little bit about function operations and composition. We are able to add functions, subtract them, multiply or divide them, and it's pretty much what you would expect. You could actually take the two functions and then you could combine like terms if you're adding or subtracting to end up with your new function, your function that has had the operation of addition or subtraction on it. Multiplication and division would work the same, but you have to be careful in division that the denominator would not equal 0. Now, for the types of homework problems you will see, I'm going to ask you to not only add, subtract, multiply, or divide, but to evaluate for a specific value of x. This actually gives you even more options because instead of having to add the two functions together or multiply them or whatever the operation is, to do that first and then to evaluate for x, it also gives you the option to evaluate the individual functions for that particular value of x, and then you can take those values and either add, subtract, multiply, or divide. And I think most of the time you will find that to be a faster, more efficient way to do something. So let me just show you quickly the difference between the two. If you look at A, and it's asking you to add these functions together and evaluate for an x value of 0, what I am suggesting is that you can find f of 0 first, and then we'll find g of 0, and then we can add those together. So to evaluate f of 0, I go to the f function, which says that it's 3x minus 4. So I'm going to substitute 0 in for x, and when I do that and simplify, I come up with a value of negative 4. To evaluate the g function at 0, my g function is 2 times x squared minus 1, so I substitute 0 for x. When I square that, 0 squared is still 0, and 0 times 2 is 0, and 0 minus 1 is negative 1. So if I want to add these functions together, when the x value is 0, I simply add negative 4 plus negative 1, and I get negative 5. Now, if I had added these functions together originally, if I had just found f plus g of x, that would mean I would have 3x minus 4, and when I add 2x squared minus 1 to it, combining like terms, I would have ended up with 2x squared plus 3x, and then minus 4 plus negative 1 is minus 5. Notice if I substituted in 0 for x now, I would still get a value of negative 5. So with addition or subtraction, it's your choice. If you want to combine them first, then evaluate for that specific value of x, you may do so. But I think especially with multiplication and division, you're going to want to evaluate these individually. For example, look at C. We're not going to do example B since the only thing that's different is we're going to be subtracting and we're going to use a different value of x to plug in. But it would operate the same way that we did A. But when you look at C, if I wanted to find f times g of x, that would mean I would have to take the f of x function, which is 3x minus 4, and I would multiply it times the gx function, which is 2x squared minus 1. Now I hope you recognize that means I would have to use FOIL, and then I would have to combine those like terms before I could evaluate. It's doable, but it's going to be more work than simply finding what f of negative 2 is and what g of negative 2 is, and then multiplying those together. So if I go back to the f equation, it was 3x minus 4, so I'll do 3 times negative 2 minus 4, And if I clean that up, negative 6 minus 4 is a negative 10. Now for g of negative 2, I will have 2 times, and then I'll have negative 2 squared minus 1. Well, when I square negative 2, that's a positive 4. 4 times 2 is 8, and 8 minus 1 is 7. So f times g of negative 2 simply means I multiply negative 10 times 7, which would be negative 70. And I'm done. Now, for f divided by g of 3, that means I want to find f of 3 and divide that by g of 3. Well, if I go to the f function, that's 3 times 3 minus 4, over my g function would be 2 times 3 squared minus 1. So once I simplify, my numerator becomes 9 minus 4, which is 5, over my denominator is 2 times 9, which is 18 minus 1, and that's 17. And that would be my answer. Let's move to the next slide. Now, this example 2 simply would be the illustration of if you didn't have an x value and you had to add, subtract, multiply, or divide these functions, how you come up with a new function. And that's really what I showed you back on example A in this last set of notes that we covered. I will not ask you to do this on your homework or on a test. I just want you to be aware that you could do it. What you will be asked to do, though, is to evaluate not only with equations, but with other types of information about functions to see if you can come up with the sum or the difference or the product or the quotient. So if you look at A, notice this is the graph of two functions on the same coordinate plane. The f of x is the parabola right there that is opening down. The g of x function is that absolute value graph that's opening up. So if I were to ask you to find f plus g of 1, that would simply mean I need to find f of 1 and add g of 1 to it. Now to do that, when I look at the graph, I want to look at the f function, the parabola, and f of 1 means what is the y value when x is 1. So if I go to a positive 1 on the x-axis and I track up or down until I find the point that will be on the parabola, I'm going to end up right here. At this point, when x is 1, y has a value of 3. Now for g of 1, I'm doing the same thing, except I don't want to go to the parabola, I want to go to the absolute value function because that one is the g function. And when x is 1, I end up at this point about here. Sorry, the stylus is a little fat, so it's hard to get it in exactly the right spot. But the y value is 1. When the x value is 1, the y value is 1 on this graph. And I'm a little above there, but hopefully that's close enough to the area where you can see it. So if I were to add up these two y values, 3 plus 1 equals 4. So f plus g of 1 would be 4. Now, I could do some of these other operations. Let's skip over and do f divided by g of negative 2. Well, that means I want to find f of negative 2, and I want to divide it by g of negative 2. So if I go to my graph for the f function, when x is negative 2, look where my parabola is. It's crossing the y-axis right there. So if it's crossing the y-axis, or the x-axis, the y value is 0. F of negative 2 is 0 because the point negative 2 comma 0 is on the graph for the parabola. Now in the g function, when x is negative 2, if I track up, my y is at positive 2. So I have the ordered pair negative 2, positive 2 on that g of x function. Now this is where you have to be careful and think. 0 in a fraction, if it's in the numerator, that's okay. It will simply equal the number 0. That would be the value for f divided by g of negative 2. But don't forget, if it's in the denominator, then 0 in the denominator is undefined. So watch carefully as you clean these up. Move over to example B with our table, and let's try a different function. Let's see what happens if we do f times g of negative 1. So if I look at the table, when the x value is negative 1, that's going to be this row right here. And that means I need to find the f of negative 1 and the g of negative 1, and I'm going to multiply those together. So when x is negative 1, the f function has a value of negative 3. When the x is negative 1, the g function has a y value of 2. So if I were to multiply negative 3 times 2, I would get negative 6. And then one last example with these. Let's say we tried to do the f divided by g of negative 2 on this one. So that means I would find my f of negative 2 divided by my g of negative 2. And here's what I will see. If I go to this table, I'm going to be looking at the top row now. And when x is negative 2, the f function has a value of negative 5 for the y, and the g function has a y value of 0. Now, what did we say happens if 0 is in the denominator? That means this is undefined, or you could say empty set. No value exists. Let's go to the next slide. And the last thing we will do in this chapter is compositions of functions. A composition, if you will look at this little gray box, you will see what appears to be a small open circle. It's not times. It is a function within a function. So if you will look at how it's written, what it's equal to, you will see that writing it with nested parentheses might actually make a little more sense. It hopefully will be more obvious, because remember, when we work with parentheses, we work from the inside out. So this would tell us whatever value we get for x, we're going to plug it into the f function. When we clean that up and find out what that value, the y value is when x is that value for the f function, we'll take that answer for the y value and plug it in for x in the g function. And I think once we do an example or two, you will understand and it won't seem that complicated. So we have two functions given to us, the f of x and the g of x here. And you have to be very careful. The order this composition is written in is critical. We always have to evaluate from the inside out. That means that whatever function is closest to the x value is the one we have to find first. So we're going to have to find out what g of 2 is, and we'll take that answer and we'll plug it into the f function for the second part. So my g function is 2 over x. That means when I plug in 2 for x, I get 2 over 2. And g of 2 has a value of 1. What we will do now is take that, and we've got to plug that in to the f function. So we're actually finding f of 1 now. So you have to do your inner function, and the value you get for it gets plugged into the outer function. So now, if I go to the f function, that's the square root of x plus 4, so I'm going to put 1 in place of x, and that would give me the square root of 5. Okay? Now, just to show you, the order matters. If I had tried to do g of f of 2, I would not get the same thing, because that would mean I would need to find f of 2 first. Now, if I look at the f function, That's the one with the radical. And that would mean I would have the square root of 2 plus 4, which is the square root of 6. I would then have to take this answer, plug it in to the g function, and I would be looking for g of the square root of 6.